Namaste and Shubhodaya. Welcome to the day 3 of our Vismaya Vigyana YouTube live lecture series, Seismic Sounds in the Sky by Dr. Siddhartha Muthuvijayan. We are thrilled to have you join us for this deep dive understanding the science principles behind this topic. Without any further delay, I welcome Dr. Siddhartha Muthuvijayan into the forum. Welcome, sir.
Thanks, Ms. Pavitra.
So let's begin our sessions today,
Yeah,
day 3.
we will session. This is the last session of this talk.
So the first two sessions we kind of gave an introduction to what are the various principles which leads to this topic. So today you will explain what exactly you've been doing in this topic.
Exactly. So this is the final one where
the
core one.
The core. So let's
the
get
earlier
into
ones
it.
are fundamentals.
Okay.
So let us go into welcome all. Again, I'll start with the title. As I told in the first session, the seismic sounds in the sky, detecting earthquakes and tsunamis via ionospheric anomalies. So as I mentioned in the first session, this has many fields involved. So sound, seismology, then detection of using GNSS, all those things. So we covered so far, covered from the fundamentals. We started from waves and we explained what are infrasonics. Then yesterday we covered what are all earthquakes, tsunamis, and how that propagates in the atmosphere. So today's talk is on how are we going to detect these signals. So that's the core of the talk. How these ionospheric anomalies caused by earthquakes and tsunamis, and how are we going to detect it. So before going into this detail of GNSS and ionospheric anomalies and its detection, let us have a small recap of what we learned yesterday. That is part 2 of this series of the talk. And we started with what are earthquakes and what are all the types of earthquakes, like extension with normal type earthquake, transform and thrust earthquakes, and how this seismic energy is propagating in the form of waves like P waves, S waves, love waves and Rayleigh waves. Then how some of the earthquakes are generating tsunamis and what tsunamis are, how the tsunamis are propagating. That also we have learned yesterday. Then the tsunamis and earthquakes, when it releases the energy, that energy propagates a little into the atmosphere and it propagates in the sky, that is in the atmosphere. So that also we have how it propagates, that we saw yesterday. And when it reaches the ionosphere, it creates the ionospheric anomalies or ionospheric disturbances. So as part of that, we studied about what are ionospheres, and then we little described about an experiment done on creating artificial seismic waves and how that is getting detected in the atmosphere using aerostats. So all those things we covered yesterday, and today we will come to the core of the topic, that is detecting earthquakes and tsunamis via ionospheric anomalies. So though there are many instruments can be used to detect, so in this talk we are going to cover how are we going to use global positioning system in broad global navigation system to detect these ionospheric anomalies. So the important part is we need to know what is this global navigation satellite system before going to how are we going to detect ionospheric anomalies using GNSS. So in simpler terms, GNSS is a combination of many satellite based navigation systems. The primary one is global positioning system, then European one of Galileo, Russian GLONASS, and even Indian one called NAVIC or IRNSS, Indian Regional Navigation Satellite System. China do have one called Beidou. So all these systems are there. So it is very easy nowadays to explain what GPS is because it touches every walk of our life now. Unlike earlier when we started the work, very few will be knowing about this, but now it touches everyone's life. And if we want to, especially in the urban system, if we want to move from one place to another place, the one which we are immediately checking is our maps, Google Maps. Or OpenStreetMaps. So that actually gives the way where we are going, how to go. That is coming from map. But somebody has to say where you are or where we are. So that comes from the satellite based global satellite system, global positioning system or global navigation satellite systems. and we are using it in maps, and we are ordering things, and that's getting delivered to our location. So the location based service has improved. So this is basically the GPS satellite based positioning system, and this positioning system, what we are going to use it to detect all the ionospheric anomalies, what every day you are using in your mobile phones. But we are not going to use mobile phones, very sophisticated receivers we will be using, but basically this setup only will be used to detect the ionospheric disturbances caused by all these natural events. And this one is the satellite system, a symbolic representation of the global positioning system. There are different satellites which is revolving around us in the sky. I'll explain what it is. And from these satellites, we will be receiving the signals, and we will be having our receiver here, either on hand or fixed on land. So if we know the time of arrival or distance between the satellite and the receiver, then we can actually find out where we are. So this is the basic principle. So we are using in this signal propagation part to study the ionospheric disturbances. So let us briefly have an idea about what this global positioning system is. There are 6 orbital planes. In these 6 orbital planes, a minimum of 24 satellite has to be there, and it is actually the more satellites are there. The idea is of having 4 satellites per orbit, and this is continuously revolving, and each satellite will be having an atomic clock, and these atomic clocks will continuously generate and transmit signals at the frequency of 1.5 gigahertz and 1.2 gigahertz. We will call L1 and L2. Recently there are new additions of L2C and L5 and other frequencies too, but fundamentally this is L1 and L2 frequencies. The clock signals will be coded like C bar A code, coarse acquisition code, and precise code. In addition to that, the position of the receiver, that is a navigation message. So all these things will get modulated, and it will be transmitted from the satellite. So all the modulation will happen, and these 2 and more signals, now L5, L2C, all those things will get transmitted from this satellite to the receiver. So when the signal, this is actually an electromagnetic signal, which is nothing but like light waves, which you might have studied, and which travels at the speed of velocity of light. So once the signal starts from there and it reaches here, the receiver will generate the similar signals, and by doing an autocorrelation, we can find out the travel time of the signal from the satellite to the receiver. That is the reason we are having a clock in the satellite. So when we are sending a clock pulse from there, and the same clock will be, in a simpler terms, same clock will be there in the receiver too. And when we are receiving the signal which has been sent by satellite, the timestamp, when it reaches the receiver, we can find out how much is the time difference. That actually says what is the time delay. So in an ideal condition, the velocity, the velocity of the light plays, and then we can from the velocity of the light and the time delay, we can find the distance between the satellite and the receiver. Once if you find the distance between the satellite and one receiver, just with only one, we will be having only the distance. But our location, when we are seeing in geometry, you might have studied in the Cartesian geometry and all, when we are having an origin, we need to locate with latitude, longitude and height, or XYZ if it is 0 in the XYZ system. So 3 coordinates are needed. So this one will give only the distance. So if we have 3 such distances minimum, then we can find out that 3 variables of X, Y and Z, which can be converted into latitude, longitude and height. Typically we will be having 4 satellites here because we need to correct for the time also. So with all the 4, those in higher secondary students may be studying analytical geometry. Instead of drawing the geometry like this, we can solve these 3 equations and find out what is the location of this. So that is how the position of the receiver or a person is identified using the global positioning system. So this is the basic principle. But the thing is, when I told here, it is the velocity of the light. We all know that around 3 into 10 to the power of 8 meter per second or 3 kilometer per second. But that is an ideal condition because that goes in a vacuum. But what happens in between the satellite and the receiver, we have atmosphere. And this atmosphere is not static, it is dynamic. Our very simple principle of refraction, which we might have studied from our primary school, if not at least from the secondary school. If you put a pencil inside the glass of water, it bends. It is not bending, it appears that it bends. So that is because of the refraction, and this refraction causes because of the density variation between air and water. So similarly in atmosphere, there are different layers: troposphere, stratosphere, mesosphere, thermosphere or ionosphere. So these layers has density variations, and ionosphere is again, it is a plasma. So when the signal passes through that, it gets diffracted. So when it is diffracted, the path of the wave is longer, so it takes more time to reach. So it appears that for the receiver, instead of keeping a satellite here, it may be like this. Like when we are seeing a pencil, if we extend this line, it appears that pencil is somewhere here, correct? So similarly, the receiver will see that satellite is somewhere here, but actually satellite will be here. So this refraction actually causes the problem in identifying the position. But what we are going to do is, we are going to estimate how much it is getting refracted. From this refraction, we are going to find out the density, where density and its density variations. That is how we are going to detect the disturbances or anomalies. So another interesting factor here is, we will be using two signals instead of like one light ray. We will be using two light rays. That is, we should not say light, it is a microwave signal, L1 and L2 or more. So the reason is, this part of the atmosphere, that is the plasma state, ionosphere, is a dispersive media, meaning the velocity of the light on this medium, or it refracts as a function of frequency of the light wave. So it refracts differently, or the delays will be different for a different frequency. So if we are using two different frequencies like this schematic what we have given, we can easily combine and find out what is the density variation there which causes this refraction. So that is the whole idea of the correction. So this principle we are going to use to detect the total number of electrons in the ionosphere. So that is a representation of the nature of the ionosphere or density of the ionosphere. So this is the equation involved to find out how we will be taking two different frequencies and invert it to find out the total electron content. So I'm not going into the details, just to give the glimpse how we are doing it. And this schematic, actually it gives that, imagine just take one signal, and this signal comes, and this is the ionospheric region, and the orange one is the region where the maximum ionization happens. So it pierces this region and it comes here. So during this path, we will be using two different signals to find out the number of electron content and its variation here. And the point where we will be taking this measurement, we will call that ionospheric pierce point. You see the receiver is somewhere here, but we will take this ionospheric pierce point. Here we will be detecting the density of the ionosphere at this point, despite we are having the receiver here. So actually this projection of this will be here. So the idea is, if any disturbance happens and propagates here, it disturbs the ionosphere at this point. So though the receiver is here, we will be detecting the distance at this point. So this point is, we will call that as sub-ionospheric pierce point. So all the detections, we can actually have it in a wide range, depends upon the angle of elevation and where it actually looks the satellite. So as I have explained yesterday, this ionosphere is very dynamic. It has regular variations, very systematic, because of the movement of the rotation of the earth and the variation of the sunlight and other physical phenomena. So like this is called equatorial ionization anomaly. It creates the crust of this. And in addition to that, solar weather and many other factors creates the disturbances in the ionosphere. First, we need to find out what is the regular variations in the ionosphere, and that regular variations need to be removed to find out the disturbances caused by earthquakes, tsunamis or other forcings which is from the ground. So this is one example which we have computed at CSIR 4Pi using the observations taken all over India. It's very limited observations, not very dense observations, hardly of 10-15 stations installed all over from here to the south to north longitudinal line, and few stations in the east and west also. All these tracks actually shows the sub-ionospheric Pierce point of different satellites which was tracked by the receivers, which is represented in a red triangle. So this is the track, and if you see that here, so this is over the Indian region, zoomed portion of this, you could see that very high electron density. This color scale actually shows that red is very high electron density, which is measured in terms of TEC unit or total electron content unit, which is nothing but 10 to the power of 16 electrons per meter square. So this is the vertical electron integration in a column of the ray which passes to it. So this actually shows the phenomena of equatorial ionization anomaly. This is from the model. You have seen that. This clearly follows, and why it comes is because you might have all studied about the motor and electric motor and electric dynamo. So if you are having an electric field and a magnetic field that is always perpendicular to each other, so if you induce or if you disturb it perpendicularly, like Fleming's rule, vertically the forcing will be up. So similarly, Earth's magnetic field and the electron mobility electric field will be perpendicular and it will be moving up. This is called equatorial electrojet. So from the equator, all the electrons are pumped up like a fountain, and it falls on the two crusts like here. So it forms the crusts here. So where high density electrons will get accumulated here. So this is one such representation which we measured. And as I said, this is a regular day-to-day variation. In addition to that, our sun is always active, very active, and solar flares are coming out of our sun. And this solar flares travels and it's supposed to affect Earth. Unfortunately, the magnetic field of the Earth protects us from these harmful solar flares, and it deflects that away from the Earth. So in this process, the Earth's magnetic field is getting disturbed, and a few portion of the solar particles, that heavily ionized particles, leaks into this portion, that is the polar regions. That is why we are seeing aurora. And this disturbances, geomagnetic field will get disturbed, and we cannot normally sense it, but what happens is all our mobile phone signals or any of the satellite communications, radio communications, everything will get affected, because all these communications either has to pass through the ionosphere or normal radio communication has to get reflected from the ionosphere. So the changes in the ionospheric condition affects. And now, since we are using positioning systems, global positioning systems or GNSS for our day-to-day applications, these disturbances of the ionosphere will affect our positions too. And one such case we studied was the St. Patrick's Day geomagnetic storm. So major storm occurred in the year 2015 in the March, middle of the March. So this is the projection of the Earth on the top. This is the northern hemisphere. You might have studied in your primary and secondary section about looking the geometrical shapes at various angles. So if you are having a sphere and this is a top view, if you are looking at the top, what you will be seeing a circle. So this is one such a circle. This represents the northern hemisphere. So the center is the pole, North Pole, and all the dotted points or the index which shows, which is computed from the total electron content which observed using GNSS receiver. So we used around 13.5 million microwave ray paths, around 2,800 GPS stations, 2,365 ground stations from observed from 32 GPS satellites for 2 days, 17th March and 18th March. And each one is at 0 UT, 4 UT at the UT time, GMT time scale. So you can see that when the geomagnetic storm occurs, the red is the highest disturbance, highest Rothe index we will say, the highest disturbance, and this is getting recorded. So this is one such global phenomena we could observe. The reason for doing this was all these kind of disturbances need to be segregated out if we want to know the feeble signatures which is generated by earthquakes and tsunamis, because these are all very strong signatures. So that is the challenge in this research. So we should be aware and we should know how to remove this out to find out the disturbances caused by these two events. So now let us go for detecting the first we will go for the tsunami induced ionospheric disturbance, detecting the tsunami ionospheric disturbance. Then we will go for the detecting disturbances using caused by earthquakes. So before going for this detecting tsunami induced ionospheric disturbances, we should know why should we do that. Always when we are studying something, either in our classroom or when we are taking this research, we should know why, what for we are doing this. See, this is one interesting analysis done by my PhD student, Dr. Shimna. See, this part, you can see that this is the number of fatalities caused by different natural hazards. You could see that the rainfall, floods, rainfall, cyclones and droughts caused major fatalities in earlier era, that is 1990 to 1980. If this is the data plotted from 1900 to 1980. So the major cause for the human death was because of the weather events. But this is from 1980 to 2019. Now you could see that this part has drastically reduced. But what is more is earthquake. Earthquake means earthquakes and tsunamis together. The reason for this is now we are having a very good system of predicting the weather, the cyclone predictions, all those things. We are forecasting the weather events is very good because of the advancements in science. But unfortunately, forecasting or predicting earthquakes and tsunamis are still a challenge because the recurrence interval, recurrent time of such events is very high. And we are having very less number of observations, and we are still trying to understand the exact physics of this phenomena. And these efforts is to understand that physics, and time being, instead of, though we cannot predict these earthquakes and tsunamis, we can try to give an early warning. Early warning is the sense the event occurred at some time. After occurrence, we can detect quickly, and we can at least warn the people that something is happening, you please move away or protect yourself. That is the idea. So that is why we are looking for various avenues, and this is one such avenue. So that is the importance of this study. That is why we are doing. And currently, other than ionospheric, we are having a conventional tsunami early warning system. So that is, as I have mentioned in my previous talk, when the tsunami propagates in the deep ocean, we cannot find its amplitude. But the conventional systems are having transducers anchored in the seafloor, and it actually connected with the buoy. And this detects the pressure variations, like sensing the variations in the pressure at different locations it is installed. And that actually detects the major wave propagation here in the deep ocean. And that sends the signal to the satellite, and that receives to the control center. So the idea is, first an earthquake has to occur. They will be having that. If there is an earthquake, what type of earthquake, and whether it can generate the tsunami, and are we sensing the signals soon after the earthquake? that is the pressure variations within the ocean. So that means the tsunami is propagating. Then we are collecting that information and getting it to the ground station. And from the ground station, we are sending the warning. And this works more or less well, but still there are challenges. The mainly thing is there are many false alarms are there. So the human tendency is the moment we get more false alarms, then when the real alarm comes, we may not pay much attention to it. So we need to reduce the false alarms and we need to improve the accuracy. So this system need to be strengthened. So we are just trying to look whether the tsunami based systems, ionosphere based tsunami detections can anyhow improve on this part. So this is the other work which is my postgraduate fellow did during her PhD. So this is the satellite, GNSS satellite. When it comes, see for example, this is the source where the earthquake and tsunami generated. This is the Japan Tohoku case. And when this propagates to the ionosphere, when the signal passes through this, from here we can detect it. So basically from the land we can see inside the sea and we can try to find out the propagation of the tsunami. So this is the case of Indian Ocean tsunami. I think, can you click on that, whether it comes? So no, leave it, it's okay. So please go into the full slideshow mode. That's okay. Good. That's okay. Leave it and slideshow mode. Okay. Leave it. So there was a tsunami animation. Sorry that it's not playing. So we will be finding out these disturbances here, what it causes in the ionosphere, and filtering out the disturbances which is caused above the sources above the ionosphere. So this one is our work by my PhD student Dr. Shimna. So during the 2004 tsunami, you can see that the right panel or this panel, you can see that the tsunami actually propagates. Tsunami starts and the earthquake, yellow star is a earthquake and it propagates here. And this is the track of the GPS satellite and it detects the disturbances here. This is the primary one, and here you can actually see that the tsunami, it started and it gets diffracted around this corner, around the peninsular India, and it goes into the Arabian Ocean. So when it comes here, from the receivers, actually receivers are lying at this point here. Bangalore, Hyderabad, Bhopal, Trivandrum and Kodaikanal. So these are all the receivers. So we used these receivers to sense the tsunami, which is around 700 or 800 kilometer away. We never had any system on the coast at that point of time, but in the post-tsunami analysis, we could see that we can really detect it when it passes through that. So this is one example of the detection. And interestingly, this actually shows that what is the velocity, because it is not only just detection, we find the velocity of the ionospheric perturbation, what frequency it lies. So all these analyses were carried out and it matches with the signal of acoustic gravity wave frequency range. So this is a proof that the acoustic gravity wave tsunami is propagating, inducing acoustic gravity waves in the atmosphere vertically up, and that acoustic gravity wave is disturbing the ionosphere and that could be detected, and the disturbance is propagating with the velocity of the matching with the velocity of the tsunami. So all these analyses were done to ensure that these disturbances are caused only by the tsunami. And another one interesting factor what we found was, usually this tsunami happened on 26th December 2004 early morning. It is around 6 o'clock in the morning, and it reached Indian coast, the first touch of that, in around 2 hours. Around 8:30 it reached. And it didn't stop there. It continuously propagated. It propagated all over the globe. And it reached, after it reaching the African coast, that is by the time it was night time in Indian region, and it got reflected back. So a small portion got reflected back and it traveled in the opposite direction, that is towards the source. So we were actually exploring what about the disturbances caused by that tsunami, because that amplitude is very small. See, the idea is using this natural event, because we cannot do the experiment, because we cannot generate that massive energy. So when the natural event happens, we are just taking it as an experiment and we are just trying to find out what happens. So that's such a feeble thing. And another interesting factor is this happened during the night time, where the ionization in the ionosphere was very less. In the daytime it is high, in the night time it is very, very less. So how the ionosphere behaves and how the significance of such a small amplitude tsunami when it propagates during the night time. So for that we took up this study, and it clearly shows that the disturbances, the snapshots you can see from left to right is actually from 16 UT to 19 UT. So at different time snaps, you can see the blue lines, which is actually the propagating of the tsunami, reflected tsunami. You can see that it propagates in this direction and it reaches here. And on the same direction, the ionospheric disturbances are reaching in the opposite direction. So this is another proof that even the amplitude is very small, we could detect the actually it induces the acoustic gravity waves because it's a function of the wavelength. These are all very high waves, and we could do that, and we did that. And next, let us move to the ionospheric signatures of earthquakes. That is, the earthquakes generates acoustic waves, and Rayleigh waves generates acoustic gravity waves, and all these two are moving up in the ionosphere, in the atmosphere, and reaches the ionosphere and disturbs the ionosphere. So we call technically that as co-seismic ionospheric disturbances. Just see, this is the case of 2015 Nepal Gorkha earthquake. So you could see that the earthquake happened at this location. This is the epicenter. So this is again satellite tracks. So after the earthquake, it generated the acoustic signals disturbed the ionosphere, and we could detect that. And this is the time series, basically plotting that with respect to time and the amplitude of ionospheric disturbances. And these are all the station names. You could see that it's a very clear signature. This is this line, blue line, actually the time of the earthquake. So after the earthquake, with the velocity of sound, the signal travels, the energy travels at the velocity of sound, and it reaches at different locations. And this is typically similar to seismograms which we are recording on the earth, on the ground. So this is how the energy pulses based on that amplitude. We found out this not only on the epicenter, how the rupture happens. This actually mimics the rupture of the earthquake. I think this is again another animation. Unfortunately, it is not playing, but it shows that over the time sample how it generates the CIDs, that is co-seismic ionospheric disturbances. Yeah, this is another case, recent case. Last year February, in Turkey, Syria, 2 earthquake happens. The reason why I am posting this is the previous one, Nepal earthquake, was a thrust event. That is, there will be a lot of vertical movement in there. So that creates. So general belief is that the thrust and normal events generates more disturbances in the ionosphere, but strike slip events will not, because that just transforms. So that may not throw up the atmosphere, so it will not create much of that. But we took up 2 studies. One is the major strike slip earthquake happened in 2012 in Indian Ocean, which I didn't show here. And this is the recent case where doublet earthquakes, that is 2 earthquakes happened one at 7.8 and another one is 7.5. Two earthquakes happened in Turkey in a short span of time, one in the night and one in the daytime. So this extensively we studied, and this is just these figures. This is 7.8 earthquake, first earthquake, and this is the second earthquake. This shows that how the ionospheric disturbances are caused by these two strike slip events. So this is another example of that. So and further we are studying that how the earthquake rupture process and the energy release is comparable with the ionospheric disturbances which we are observing. So such studies are still going on. So much need to be studied on this to understand the phenomena, because now the more and more observations comes from GPS receivers, and in future we may be using the GPS receivers which we are carrying in our mobiles. So we will get more dense observations, but there are challenges how to use that for this kind of scientific studies. So these gaps need to be addressed. So the more amount of work need to be done, and this challenges throws a lot of opportunities to carry out more research in this thing. The interesting part is this will be useful for remote sensing of earthquakes. So far we are observing the earthquakes on ground. So our limitation is we will be keeping seismometers only on the ground, and very specifically specially designed few seismometers are placed on the sea floor. But again, we have to anchor it on the ground. So that gives a limitation in studies. If we are successful on this, we can remotely sense earthquakes. There are few attempts which actually we can actually use the payloads in spacecrafts so that we can study Venus or any other planet for that matter. We can remotely sense earthquakes of those quakes of that. We should not say earthquakes, but quakes in that planets, which still it is elusive. This actually throws up the opportunity to do that, and tsunami early warning can be done, monitoring nuclear tests can be done, and rocket and missile launches disturbances can be tracked. Even cyclones generates acoustic gravity waves. This can be, all these things can be tracked. So this is the, now we have concluded all the three part, but this is the interest of an interdisciplinary research. We have started from waves and we came to earthquakes, and finally we came to ionospheric anomalies. Hope the students might have got the glimpse of what are all the principles we have used. See, starting from waves, and then we talked about different geometries, elevation angles, all those things. That starts from geometry.
Yes.
We didn't put mathematics. We don't want to make it very complicated. We wanted to put it in simple. If you put a wave equation, you will know that a trigonometry is very important.
Yes.
And then we started with, for positioning, we showed that analytical geometry. So geometry, analytical geometry, and solving linear equations, which comes from matrices and determinants, and different principles of physics starts from, even if you want to study earthquake, elasticity and other things are needed, how the energy propagation goes on, and how the refraction happens, and much more. When we are, I didn't give much of details in the ionosphere because it is a fourth state of matter, plasma, and how in the plasma wave will propagate, how electrons will behave when we are pushing the electrons in which falls in the electric and magnetic field, how will be the dynamics and motion of that electron. So this involves, and when we are talking about ionosphere, what kind of atoms are there and what kind of gases are there, whether all gases are there, how much oxygen, how much nitrogen, and when the X-ray or solar radiation falls, how much energy will be needed to ionize, whether these energies will be uniform all over the all the period of entire all around the year. A kind of geography is needed. So when we are studying our chapters, there is a general say that it will be very boring and we will find it very much complicated.
Yeah.
And we used to say that when even starting the Newton's law, there is a famous caption, when an apple fall on Newton's head, Newton found out these laws, and students used to say that instead of apple, the tree itself would have been fallen, our life would have been much more easier. But if it is not Newton, somebody else would have
found
studied,
it. Yeah.
found out. So there is no escape to it. So if we understand the applications, the entire idea of this is the students should understand the applications, how all these theories are being used in the real life phenomena, and how we can improve the human life. That is the entire idea. So I request all the students to understand its applications, and over the period you will come to know. So all the things which in our lifetime, from the class 1 to even higher degrees, and even after that, all our learning will be useful, and we should understand and learn instead of becoming answering machines. The very important part, which before going to thanks, I would like to say that in the era of artificial intelligence, now we have generated machines to answer. The interesting part, or what is needed, is who will ask questions. So we need people to ask intelligent questions to these artificially intelligent machines. So to ask intelligent questions, we should understand the principles, we should understand the applications and all those things. So understanding is very much important. So hope this talk would have given a little bit of understanding on this particular field, an interdisciplinary field. Thanks a lot. And I thank, at this outset, I thank my PhD student Dr. Shimna and postdoctoral student Dr. Danya of contributing these plots and analysis. They have contributed to that along with me on this ionospheric detection of disturbances caused by these natural events. Thanks a lot.
Thank you, sir, for that mind-blowing talk. You just showed them how interdisciplinary science works as along, and it goes hand in hand with maths. We take each and every stream of science and each and every stream of mathematics and combine to give a useful application which will serve for the goodness of the society. Thank you for that. You nailed the initiative's purpose.
Thanks for this opportunity.
Thank you everyone for joining us today. This concludes the 3-series YouTube lecture of the Seismic Sounds in the Sky. Tune in to us every month to hear such good talks on different topics of science. Thank you very much. Have a nice day.